So, welcome to Practical Auth for Developers. Over the next hour, I'm going to take you on a guided tour of 10 different authentication and authorization techniques. At the conclusion of that hour, assuming you stay awake, you'll leave this room with a fundamental understanding of how those techniques work and when to use them. And our journey begins with a confession. So a few years ago, I made a huge rookie mistake. I was writing a feature, I needed a piece of JavaScript to make an API call back to my server. The server needed to know who was making the call, so I did a search for how to authenticate an API call. I found a really confusing mess. There were all this stuff about bearer tokens, nonces, federated identity systems. There were Reddit fights over the correct cryptographic hash function to use when signing a request. Two different things of this thing called Auth. People were fighting over which version was better. And this thing called JSON web tokens that some people said were God's gift to the internet and other people said were a scourge on all mankind. So it was totally confusing. I was in a hurry. I cobbled together some code from Stack Overflow, and spoiler alert, I shipped a defect. So my goal today is to give you that coherent overview that I desperately needed back then. I'm going to break down all that complex terminology. I'm going to compare and contrast those techniques so the next time that you need to choose an authentication strategy, you can make an educated choice and not a rookie mistake. Now, I want to be clear about what this session is not. I am not a security expert, and this is not an advanced security session. If you already know the difference between OAuth 1 and 2, how to sign a request using HMAC, or how to use JSON web tokens to replace server-side sessions, then you're probably in the wrong place, because my target audience is the people who don't know those things, or that those are things they could know to begin with. I'm not going to show you how to implement any of these things. There are things in this talk I have no direct hands-on experience with. I've never written any OAuth code. I couldn't tell you what step 0 was if I wanted to. But what I have done is Google the crap out of OAuth. Or more specifically, I've Googled the crap out of how OAuth compares to everything else that you could do. And that's what this session is. I've packaged all that research into a coherent explanation of how these things work in relation to each other. So here's the list of topics that we'll cover. I'll teach you the fundamentals. You'll need to search out your own Hello World or Getting Started tutorial on your own. Now, before we get to that list, we need to define 3 concepts that you need to keep in mind. Let's say we have this website, and a request comes in for some URL, like foo42. The identity associated with that request is the person or entity that's making it. In this case, it's our lovely user Alice making the request from her desktop computer. Authentication is the process through which we determine that identity. It's whatever our website does to confirm it's actually Alice making the request. And authorization is the process of ensuring the identity is allowed to do the request, right? It's whatever custom business rules govern whether or not Alice is allowed to access foo42. Now, when we're talking about authentication, it's generally considered a bad idea to just blindly trust the client, right? We need some reliable way of verifying their identity so that we can differentiate between Alice and someone just claiming to be Alice. And there are 3 main factors that can be used in authentication: something you know, something you have, and something you are. So passwords are a good example of something you know, right? Both parties know Alice's password. That knowledge can therefore be used as an authentication factor. Key cards, authenticator apps are good examples of something you have, right? They're given to or set up for specific people. So being in possession of those things can be an authentication factor. And biometrics are an example of something you are, like fingerprint or a retinal scan. Those things are unique to a single human, so they can also be used as authentication factors. Today we're going to talk about the first 2 things. I'm not going to cover biometrics, but once you understand the other 2, then you'll have everything you need to understand biometrics as well. So the most common authentication factor used on the internet is a password. And I know you've all used passwords before, but I want to start here because there are 2 important things that your everyday run-of-the-mill password implementation will demonstrate for us. So here's our lovely user Alice logging into our website. And even though her password is masked out on the screen, it's included in the form post as plain text, which means it goes out over the wire as plain text. If Alice is working from her local coffee shop's free Wi-Fi, then those credentials could be visible to any attacker that is eavesdropping on that Wi-Fi connection or any part of the internet between her and our web server. So if you use TLS on your login forms, then the network connection between Alice and our server is encrypted. That prevents anyone eavesdropping on that connection from getting access to her credentials. So encrypting the contents of the entire request, TLS provides security in transit because that sensitive information is protected as it moves across the internet. Now the key thing about encryption is that it's reversible. And that's kind of the point. The sensitive information has to be turned into gibberish as it leaves the browser, travel across the internet as gibberish, but then the web server has to be able to turn it back into something it can recognize. So this reversible encryption is the first concept I wanted to illustrate using passwords. The second thing comes up when we talk about what happens on the server when we validate the login request. So the simplest thing that we could do is throw all of our passwords into our user database as plain text. And if we did that, it'd be very easy to validate a login request, right? We would just query the database for a user record with that username and password. But if we're storing the passwords as text, we're not providing security at rest. So if anyone happens to get a hold of our database file, they have access to all of our user passwords, and that's very bad. So we could apply encryption here as well, right? We could encrypt our passwords and store the encrypted version in the database. And if we did that, the login verification would be just as easy, right? The app would just encrypt the password before querying the database. But there are two reasons not to do this. The first is that our website has no legitimate need to know what Alice's actual password is, right? We do need some way of validating it on login, which we'll talk about. But otherwise, we don't need to know what the actual password is. And if an attacker is able to access our database file, then there's a decent chance they've been able to access our encryption keys as well. So if we're storing a reversible encryption value in the database, an attacker has the potential to decrypt it and get access to all of our credentials. Again, that's very bad. So to address those issues, we can use hashing functions. This is the second concept I wanted to illustrate using passwords. So hash functions are similar to encryption, and in both cases, you pass some sensitive string into a mathematical function, and it gives you some gibberish string as output. The key difference is that hashing a value is a one-way trip. That hash value cannot be reversed into its original string. An encrypted value can be reversed as long as you have the encryption keys. So that means that storing the hash in the database is more secure than storing the encrypted password because there's no other detail that an attacker could steal that would allow them to reveal passwords at scale. Additionally, hash functions convert every unique input into a single deterministic unique output. So no two passwords put through the same hashing function will generate the same result. So therefore, we can store the hashed value of a password in our user database. So the web server receives the request, it takes that plain text password, hashes it, and then searches for that result. And if it gets a hit, it knows the user entered the correct original password. But at the same time, our website has no way to actually reverse engineer it back to Alice's actual password. That makes it much, much harder for an attacker to steal credentials at scale. Now, I am oversimplifying things here a little bit. There's things like salting your passwords. There's rainbow table attacks. Lots of stuff that you need to know about. But the simplified example is enough to illustrate how hashing functions can convert a sensitive value into a less sensitive value. And that's going to be a recurring theme throughout this talk. All right, so that covers how we authenticate the login form post itself. But what about what happens next? So Alice logs in, and then she submits her request for foo42. Now, by itself, this request doesn't tell us anything about the identity that's making it. So how do we link it to the identity established during her prior authentication step? And there are primarily three ways of doing that. For an interactive website, the most common approach is for the web server to keep track of authenticated sessions, and it sends a cookie to the browser when someone logs in, and that cookie gets resubmitted with all requests sent back to the server. The server then can use that cookie to link that session with some server-maintained state. And this all happens automatically, right? You don't need to do anything. This is just kind of the foundation for how most web frameworks work. Now, if you don't want to use cookies, or if you can't, we can also send credentials through HTTP headers, and we'll come back to this in a minute. There's also this thing called X509 client certificates. So these certificates are basically like reverse TLS. So if you're using TLS, there's a certificate stored on the server, and that certificate tells the client the server is who it claims to be. It's the foundation for your browser knowing it's talking to your bank and not some bad guy website pretending to be your bank. Client certs are installed on the browser, and they tell the server the client is who they claim to be, right? It's just the inverse. So client certs are a really nice option if you can get people to use them, right? This works great for like a small internal application. It doesn't really scale to the public internet, so I'm not going to talk about it a lot here, but it's something that you should know about in case you happen to fit that use case. So passwords and session cookies are great for like a user interactive session when there's a person at the other end of the request. But what about computer-to-computer communication, right? You have one web app that needs to call an API endpoint on another app. We can't redirect to a login screen because there's no one there to interact with it. So in this case, we can use something called basic authentication. This is an internet standard. It describes how to send credentials via an HTTP header rather than a login form. Now, the name of the header is authorization, which can be a bit misleading. There are a few different ways to use this header, but when it's used like I'm describing here, it's being used primarily for authentication, not authorization. And here's how it works. To follow the basic auth standard, the value of the authorization header consists of two different pieces. The first is the scheme, and that tells us how to interpret whatever comes next. So for basic auth, that scheme is just basic. When the scheme is basic, then by definition, the rest of the value is a base 64 encoded credential pair in the format of username : password. So basically, when the client still needs to know the username and password to use for authentication. To make an authenticated request, the client concatenates those things together, and base 64 encodes the string. The encoding process results in some string of gibberish, which is then put into the HTTP header. The key thing to remember is that encoding isn't encryption, and encoding isn't hashing. Unlike the hashed values we just talked about, this gibberish string is 100% reversible to the plain text credentials. No special key required. Encoding is about making a string easier to transmit. It has nothing to do with securing the value. So therefore, you got to make sure that you're only sending basic authentication over a secure connection, right? Because just like with passwords in a password form, if an attacker can eavesdrop on the connection, they can steal the credentials. So basic auth supports some automated scenarios, which is really helpful, but it still requires knowledge of a password. And there's one big issue with using passwords for computer-to-computer communication. That's namely that passwords are their primary account credential, right? They are the key to the user's entire kingdom. If you forget to use TLS, or if TLS gets cracked like SSL did before it, an attacker can steal that password off the wire, they get total access to the account. Let's pretend that this foo42 endpoint returns some basic, non-sensitive data. We want to require authentication, maybe so we know who's calling it or for rate limiting or whatever, but the contents of the API itself really aren't terribly private. It would be bad practice to require the primary account credential in order to access that relatively unprivileged information, because the risk of losing the credential far outweighs the value of securing that endpoint. So instead of using full account passwords, consider using API keys as a sort of like limited privilege, usage-specific password. So for example, maybe our app lets Alice connect it to her social media accounts. So those apps can then get some of her data from our app. Instead of having those apps send her primary password to us in a basic auth header, we could create separate credentials for each of those services. And we could authorize those credentials with very limited permissions. That way, if someone were to compromise her Facebook integration with us, it would not compromise her Twitter account, and vice versa. And additionally, API keys like this could be used only for API calls, right? We could prevent someone from logging into the account with them, which limits the damage that someone can do if they compromise the key. And there are two ways of doing this. One way is to pass the API key as a bearer token in an HTTP header. Bearer tokens are like cash, right? They aren't restricted in any way. Anyone that presents that token is allowed to use it. So bearer tokens like this are passed as plain text so that the server can then read the value and validate it. If you care about internet standards and interoperability with a wide variety of clients, then you might want to look at using the authorization header with the bearer scheme, but you can also use custom HTTP headers like XAPI key. Right? It's totally fine, depends on what your audience is. There's no specific format governing what an API key is. It's not a standard, but the set of possible values has to be large enough that it can't be easily guessed or attacked through brute force. So some sort of GUID is usually a good starting point. The larger and more random the values, the better. Now you can also pass API keys as query string arguments, but if you do that, then they're going to show up in your web server log files. And you wouldn't normally want user passwords to show up in your log files. In this case, the API key is effectively a password, so it's generally worth the effort to use headers instead. The other way of using API keys doesn't require sending them over the wire at all. This technique is called signing the request, and it uses an API key in conjunction with a hash function to create a cryptographic signature for the request. That sounds kind of mathy and complex, but it's really not. Here's how it works. The client still has to know the secret value. In this case, it's the API key, because we're still talking about something you know, authentication factors. When it's ready to make an authenticator request, the client prepares the message it's going to send to the server. This would be the URL it's going to request with any particular query string parameters or foreign values that are going to go into that request. It then concatenates that message with the user-specific API key. That creates a string that's unique to Alice. Any other client trying to access the same URL but for a different user will get a different string because it will be using a different API key. The client then runs that string through a hashing function, which creates a unique signature for the request. The string being hashed is unique to Alice's request for that URL, and hash functions return a unique output for every unique input. So no other client will generate this signature unless it's using Alice's key to request this exact URL. So the client then makes its request to the server, and it sends that signature as an HTTP header. Now, the API key itself is not included in the request. It does not go over the wire. It was used to create the signature, but the hash value can't be reversed. So anyone who captures that request off the network will be unable to extract the API key from it. Signing also protects requests against man-in-the-middle attacks. So let's say this bad guy has managed to infiltrate some part of the internet that this request is going to go through on the way to our server. he wants to try and change that request or some part of it before it's received by our server, right? Maybe he wants to change one of the parameter values so that the server gets a different request than what the client submitted. Real world example might be if Alice is transferring money from one of her accounts to another of her accounts. If some man in the middle can change the target account number to his own account, he might be able to trick the server into sending him the money instead. But when the server receives the request, the first thing it does is look up Alice's API key. It then recalculates the signature using the request it received plus its copy of Alice's key. If the request was altered in any way while in transit, those values won't match. Now, those values don't match, the server knows it can reject the request. If they do match, the server and the client both used Alice's key to hash the exact same request, so the server knows it's talking to Alice and the request was not modified in transit. Now, I glossed over one important detail in that explanation. The whole process depends on the server using Alice's key to validate the signature. But there's nothing in that request that identifies Alice as the originator. So how does the server know to use Alice's key for validation? So when using API keys to sign requests, your request needs to indicate the identity and the signature. This is very similar to basic auth, which works in very much the same way. So what should we use as the ID? Right? You could use some primary key from your user database, like an email address or a user ID or a username or whatever uniquely identifies someone in your system. And that works fine unless you want to allow people to create multiple API keys. If you support multiple API keys per user, but you only pass the user ID in the header, the server will need to try each of those keys in sequence until it finds a valid signature. That could potentially be a lot of unnecessary overhead when you're handling a request. So a common solution is to issue API keys as a key pair, containing a public and a private component. The public key is sent in the header as plain text. That value has to be unique in our database, so the server can take it and then look up the corresponding private key, which is then used to validate the signature. So this concept of concatenating some string with a private key, running the result through a hash function, and sending the result or the output as a signature is the foundation of pretty much everything else we're going to talk about. It's so important it has its own acronym. So the signature is an authentication code. It's created using a hash function and is used to validate a message. So it's called a hash-based message authentication code, or HMAC. So if you see this term anywhere, it's just referring to this sort of signing process where a shared private key is used with a hashing function and is not sent over the wire. There's one key thing to remember. In order to use API keys, the client has to know the key. Right? That means the client needs to store the key somewhere between requests. For server-to-server communication, this is pretty easy. Right? We generate some key for Alice, we put it in our database, and then some developer for the client application comes along, and they get the API key from us in some secure way. Maybe it's over secure email, maybe they download it from our website, whatever. The point is, some person is responsible for obtaining that key in advance and then storing it on the client application, like in a configuration file. The client app can then use that key to sign requests, as a bearer token, or whatever it wants. But what if the client isn't another server, but it's one of those newfangled JavaScript things written in React? So maybe Alice goes to her local library on a Sunday afternoon and logs into your app from a public computer. There's no way to preload her API key on that machine in advance. But without it, your React app can't make authenticated requests. So we could have Alice sign in with her password, and then we could send the API key back in the response. But there just isn't any way for your JavaScript client to store that key between requests. That's because JavaScript is an insecure environment. Its crypto functions can be monkey patched and replaced with compromised versions. Local storage can be attacked through cross-site scripting, etc. The rule of thumb is that any data you expose to JavaScript is open to inspection by malicious scripts. We cannot make the API key available to our JS code without making it visible to attackers as well. So if we're working with a JS client, we need some technique other than API keys to handle authentication. One option to do that is JSON Web Tokens, pronounced JOT. I often say JOT tokens, which is the same like linguistic mistake as saying ATM machine, but I can't stop doing it, so I apologize if that bothers you. You're going to hear it. Anyways, here's how they work. In a JOT scenario, the server has a system-level private key that it keeps to itself. That key is not shared with any clients, and it's not user-specific, right? It's a system-level key. Now, a user is still required to authenticate via some mechanism like a login form. Web tokens don't replace that step. They just provide a secure way of representing that a user has been authenticated. So after the user is authenticated, the server constructs a JSON document of claims about the user. And claims are just pieces of data, right? Like stating the username for the current user is Alice. The server then signs those claims using the same technique we saw earlier, except this time the claims are being signed with the server's private key, not a user-specific key. That creates a signature that can be used to validate the claims. Finally, a token is created that contains the plain text claims plus the signature. Again, the server's key not included in that token. Token is sent back to the client as part of the response. Client then sends the token back to the server with all subsequent requests. Server gets the request, recomputes the signature with its own private key, compares that value to the signature in the token. Right? If they match, then the server knows the token was signed by its own private key, so the claims in there can be trusted and were not modified in transit. So the server can then authenticate this request as coming from Alice. It's similar to how server-side sessions work. With a server-side session, every request contains a cookie with an ID. That ID is a pointer into some kind of session memory on the server. It maintains state that way. The difference is that with JSON Web Tokens, there is no additional database of session information. Each JOT token is a self-contained set of claims. So in the simplest case, the claims will simply identify the user attached to the request. This is authentication only. Everything else is up to your app. So if you need to know, for instance, if Alice is a member of the administrator group, you would have to write a query to look up her roles or permissions or whatever from your database. But web tokens are interesting because they can help you with authorization as well. Rather than running a query to see if Alice is an administrator, you can include that information as an explicit claim in the token. These claims are signed by the server, so they can't be modified in transit. No one can give themselves admin access. And you can include whatever information you want in that token. You can even include very granular permissions if that makes sense for your application. This can be really helpful if your app gets a lot of traffic, because you can potentially avoid lots of repetitive database queries during your authentication and authorization process. Now, there's one very important trade-off that you need to consider if you want to use JSON Web Tokens. You can either store sensitive information in the claims, or you can make the claims visible to your JavaScript application. But you can't have both. If you expose the claims to your JavaScript, you're also exposing them to any malicious script that's running. So if your app can read the claims, so can the bad guys. So in practice, there are two places where you can store your web token between requests: local storage or an HTTP-only secure cookie. If you put the token in local storage, then your JavaScript app can access the full token and read whatever claims are in that JSON file or string. But local storage is susceptible to cross-site scripting. So that web token can't contain anything sensitive that you would not want falling into an attacker's hands. If you store the token in an HTTP-only secure cookie, then that value, the cookie value, is completely invisible to JavaScript. So it's safe from cross-site scripting. You can put sensitive information in the token. You just can't read it from your client-side code. So I used a JS client as an example, but JSON web tokens work for server-to-server API calls as well. They can also be used for single sign-on, at least in some simple cases. So let's say that you manage multiple web applications. They both have access to the same private key. Alice could authenticate to server 1 with her username and password. That'll get her a web token signed by that key. She could then go to server 2, pass the same token, and server 2 will validate it and be able to trust it and authenticate her. That way, she signs on once. That authentication will apply to both servers. That's why it's called single sign-on. Now, one word of caution, though, is that the stateless nature of web tokens can be a double-edged sword, because that token is effectively valid for as long as the server can validate the signature. But what if Alice's access level changes? Maybe she had admin access when she first authenticated to server 1 and she got the token, but then since then she won the lottery and she quit her job. Peace out. As a result, her account was terminated, right? But as long as her browser keeps resubmitting that token to server 1 and 2, they're going to keep validating it. And they're going to say, cool, here's your admin rights. That means it's very difficult to implement a sign out from everywhere type feature with web tokens, because there's no central repository of where Alice is signed into with a given token. Now, it's not a perfect solution, but assigning an expiration date to the token can help with this. Right, in this case, the server would first validate the signature, and it would then perform a second check to say, hey, is the key still valid? And as long as that expiration date is included in the signature, right, a client can't artificially extend that timeout without breaking the signature process. Now, if you recall back to the beginning, when I said I shipped a security defect a few years ago, it was similar to this. I created a way of passing a token to the server, but that token would never expire, so you could effectively stay logged in forever. So the moral of the story is, make sure you always have a plan for revoking whatever authentication or authorization claims that you sign. All right, so we covered a lot of ground. Let's take a quick breath, look back at our agenda, see how we're doing. Passwords, basic auth, client certificates, and API keys are all methods for doing authentication with user-owned credentials. Web tokens are an example of a claims-based system that uses system-owned credentials to sign a token. And it can be used for authentication or authorization, depending on how you use it. The next thing I want to talk about is SAML. And it's similar to JSON web tokens and is often used for single sign-on like we just talked about. And the elevator pitch is this. SAML is like a souped-up, enterprise-grade version of JSON web tokens that uses XML instead of JSON. Now, I know XML is gross, it's outdated, all the cool kids are using JSON, but there are mature libraries that make it really easy to implement and abstract away most of the icky angle brackets. And SAML is worth knowing about because it's still very widely used in single sign-on scenarios, especially in enterprise use cases. It covers some advanced security topics that web tokens just don't handle. There are 3 parties in a SAML scenario. The first is the user that's trying to do something, and we'll use Alice again. The second is the service provider. That's the website Alice wants to use. And the third party is the identity provider. That's the website responsible for authentication, like Google or MS365 or whatever. So Alice first goes to the service provider, and she does not have an authenticated session yet, so they redirect her over to the identity provider. The identity provider uses whatever technique it cares about to authenticate her. It then creates a set of signed claims containing that identity information. Alice is returned to the service provider, who validates those claims, uses the information in them to authenticate her. Now, for this to work, both the service provider and the identity provider must use the same value to identify a user. So if Microsoft says, hey, Alice is at alice@outlook.com, then the service provider needs to be able to link alice@outlook.com to some record in their system. So if you want to do this, you need to make sure that those identifier values are kept consistent between the two systems. Now, one really nice use case for SAML is outsourcing multi-factor authentication. Some of my clients require MFA for security and regulatory compliance reasons. But building multiple authentication systems can be expensive. I don't really want my team to focus on that. I don't want to have to maintain all of that. With SAML, we can push the authentication off to some third party. They can deal with all the testing and liability. All my app has to do is match the signed claims to a user account, which is much nicer. All right, let's talk about OAuth, which also deals with a three-party scenario. So let's assume that there's this website called Totally Trustworthy Photos that competes with Shutterfly. It offers custom holiday greeting cards with your pictures. So TTF, as I will call them for short, is very user-friendly because they will let you use your Facebook data, your pictures, to build your greeting cards so that you don't have to upload your photos directly into their app, right? Pretty standard use case. The naive way to do this would be for Alice to give her Facebook credentials to Totally Trustworthy Photos. They would then log into Facebook and get her data with her credentials. In this scenario, TTF would be making an authenticated request to Facebook. As far as Facebook could tell, it is Alice on the other end of the line, not this weird photo site. But what if TTF isn't trustworthy, right? They now have access to her primary Facebook password. They can do all kinds of bad things with that. This is why we don't want a third-party system making an authenticated request as Alice. So OAuth addresses that scenario by providing a system for delegating authorization to a third party. So basically, Alice logs into Facebook, which is where her data lives, and she tells them that TTF is allowed to view her pictures, but they can't do anything else with it. And you've all seen this before, right? You go somewhere, you get some pop-up or whatever. Hey, can so-and-so use your data? And you say yes, no, or whatever. That's OAuth. So Alice will then log into TTF, which is now making an authorized request to Facebook's APIs to get her data. And the key is that Facebook can separate who is making the request, TTF, from the permissions granted to it, like access to Alice's photos. Alice gets to make her fancy greeting cards while keeping her account data safe. So win-win. There are two different versions of OAuth. They solve the same problem, but they use two different approaches. OAuth 1 uses signed requests. It's very secure because the client and the server both know who they're communicating with, and their messages aren't being changed in transit. But signing requests can be complex. The server and the client have to do it exactly the same way. They have to agree on what parameters to sign, what order to put them in, etc. And that can be difficult to get right. The other drawback to 1.0 is that it's really only designed for web-based clients, right? This whole intermediate redirect is very specific to how a browser works. OAuth 2 was designed in an attempt to simplify those things. It gets rid of the signed requests in favor of bearer tokens, which are easier to implement, and it provides more support for enterprise and non-web use cases. Now, when I first wrote an earlier version of this talk, there was a lot of debate in the industry about which version was better. In fact, one of the guys who helped design OAuth 2 took his name off of the paper before publishing it because he felt it was an insecure and dangerous approach. But I think these days, I think OAuth 2 has basically won out, probably because of ease of use. Just keep in mind that if you're working on a highly sensitive system, the extra complexity around signing the requests might be worth it. Now, there's a key distinction that I want to make, but it will make more sense if we walk through that OAuth process in a little more detail first. So Alice goes to Totally Trustworthy Photos to make a greeting card. TTF doesn't recognize her. They send a 302 redirect back to Facebook's OAuth endpoint. Her browser follows that redirect, goes to Facebook's endpoint, and the redirect identifies the client as TTF, the scope that's being requested, and where to redirect if the authorization is granted. Facebook then uses that information to display that authorization prompt, which we've all seen. Alice says, yeah, I want to use them, give them read access to my photos. So she approves the authorization. Facebook then generates an access token, appends it to the redirect URL, and sends a 302 redirect back to Alice's browser, who returns back to Totally Trustworthy Photos and repeats her request. But this time, she has an access token, so TTF lets her in and gives her access to the application. TTF then uses her access token to call Facebook's APIs to get her data. And those API calls are both authenticated and authorized, right? They're authenticated as TTF, authorized by Alice to view her data. So the API calls are authenticated. But what about Alice's interaction with Totally Trustworthy Photos? They have an access token for her Facebook data. So is Alice authenticated to TTF? Can they be sure it's Alice on the other end of the request? And the answer is no. OAuth is not an authentication protocol. It should not be used as one. OAuth allows Alice to delegate access to her data. It doesn't allow her to log in as Alice to any website. The whole point of authentication is to securely associate a request to an identity. But OAuth access tokens don't tell the client anything about identity. The token is something the client can use to get data, but the token itself is a black box. Clients can't extract any data from the token. And if the token can't tell us anything about identity, it can't serve as proof of authentication. But what if the access token allowed TTF to call an API, and that API would give us back identity information, right? Maybe there's this get email endpoint they can call with their token, and it returns Alice's email address, right? And then they check their local user database and find an account with that same email. So the user gave TTF a token. The token let them obtain Alice's email, and that email matches an account in their system. So can TTF give that user access to Alice's account? And again, the answer is no, because access tokens do not support audience restriction. Now, before I explain that, note that nothing is wrong so far, right? It really is Alice on the other end of the request. But there's no guarantee that it's Alice. For example, let's assume that Alice has already gone through that whole OAuth flow. She's been redirected back to TTF with her access token. But again, TTF isn't trustworthy at all. So they turn around and they make a request against supersecretstuff.com. Also supports Facebook OAuth. Now the actual content at supersecret doesn't matter, but it's just definitely way more sensitive than her Facebook photos. That initial request doesn't contain an access token, so supersecret stuff starts the OAuth flow by returning a 302 redirect to Facebook. But instead of going through that Facebook auth process, TTF reuses the access token they got from Alice. So as a result, when supersecret stuff uses that token to call that Facebook API, they get Alice's email address again. And let's say that Alice happens to have an account in supersecret stuff with that same email. If supersecret stuff uses the result of that API to authenticate Alice, they have actually given Totally Trustworthy Photos access to Alice's account at supersecret stuff. Now, neither of those sites has any more access to her Facebook data than she authorized, right? They have access to her photos and her email address. But by misusing the access token, super secret stuff failed to secure her data on their site. This happens because OAuth access tokens do not have audience restriction. This is a problem with bearer tokens in general. Super secret stuff had no way to know they were being given a reused access token. That's why you can't rely on an access token as proof of authentication, even if you can trade that token for information about the identity that authorized it. Now, to solve this problem, the access token would need to include additional stuff. The access token would need to indicate what client they were granted to and which identity granted them. If the access token had that information, then Alice's token, in our example, would have been usable only by totally trustworthy photos. It would have clearly indicated that Alice was the one that authorized it, and in that case, it would have been safe for TTF to use that as proof of authentication. That token also would have had the information for super secret stuff to know to reject it. And that's basically the idea behind OpenID Connect. Normal OAuth access tokens are a black box, right? The clients can't get any data out of them. ID Connect extends OAuth 2.0, and it adds extra tokens that have a well-known format, so the client can extract data from that token. And they can extract things like audience restriction and identity claims. So normal OAuth is for authorization only. If you want authentication too, go back, there. Then you want to use OpenID Connect because you get the additional tokens. All right, so we're making great progress. We've covered a lot of single-factor authentication methods, but to close out the session, I want to explain how the authenticator apps work as well. So these apps are typically used in addition to the other forms of authentication, and they're a little bit easier to implement than you might think. I think you're all probably familiar with this kind of thing, right? You log into some system with a password, then you open some app, get some code out of it, and type that code into a web form. These are called time-based one-time passwords, abbreviated as TOTP, and there's a standard way of implementing them. So here's how it works. Alice authenticates to a website through whatever mechanism they use. It indicates that she wants to set up multi-factor authentication. The website generates a random secret key and stores it on her account just like an API key. The website will typically then display a QR code that Alice can scan. This is actually a little bit simpler than I thought it was because that QR code just contains a specially formatted URI that contains the website name, Alice's email, and Alice's secret key. The authenticator apps are associated with that URI, so they see it and they use it to add an entry into their app for Alice at their website or whatever. When Alice goes to log in, both the authenticator app and the server run Alice's secret key plus this sliding time window into the TOTP algorithm. And that generates that code that Alice types into the web form. Same concept as signing a request. If both the client and server get the same result, that means they both calculated it with Alice's secret key, and that's the basis of identity. The thing that makes TOTP different from API keys is that TOTP defines these sliding time windows. So that code resets and changes every 30 seconds or so. That increases security, but it can cause problems if your client and your server can't agree on the current time. So it's really important that like your server has a standardized time server, because if its server clock is off for the client, then you may have a hard time getting those windows to line up, and you won't get your tokens to validate. So here's the last 50 minutes in a single slide for your screenshotting pleasure. Top right corner is a link to these slides on my GitHub. At the bottom is my contact information. If you have questions, comments, or stock tips, I'm open to all of that. I have about 10 minutes, so I will take some questions from the room or from Discord. And thank you for your time. Enjoy Star Trek. I have a question already, okay?
Tony, yep. In the first HVAC example, are the private keys, the signature, one-to-one with the user or one-to-one with the public key?
So in the HVAC example, say that again, are the public keys one-to-one with the user?
Are the private keys, the signature, one-to-one with the user or one-to-one with the public key? For example, or in other words, if a user has multiple public keys, do they also have multiple private keys?
If a user, okay, so we're talking about like back when we were signing requests. Let me find somewhere back in all of these crazy slides. Where are we? Here we go, right? All right, so, so he asked, in this case, when we're using multiple private keys, are there multiple private keys and multiple public keys for the same user? Did I get that pretty much right?
Yeah, if a user has multiple public keys, do they also have?
Yes. Well, I guess that doesn't have to be, right? You could have multiple public keys for the same private key. It's kind of an implementation detail. One reason to not reuse the private key, though, is so that you can revoke credentials. So if you imagine you set this up, and at some point, the first key gets compromised, and you decide, hey, I want to just issue a new one. If you're reusing your private key, it's not going to do you a lot of good. So typically, it would be a separate key pair, both being unique, so that you can reissue it if you need to. Over here.
So when we use OIDC, would it do both authentication and authorization?
So the question is, if you're using OpenID Connect, is it giving you both authorization and authentication, right? Yes. So OpenID Connect, the authorization part comes from the plain OAuth, and the other tokens are authentication. So you get both. So you're using SAML, you're going to use SAML and OIDC? Yeah, so you could use SAML for authentication and OAuth for authorization, right? I mean, you could do it. And then maybe if you're doing single sign-on to a third party, the SAML would cover that part, right? So that Google tells you who the user is, and then you would use OAuth with your client to do the authorization part. They can be done completely separately. Yeah, OIDC could do both. I mean, it comes down to kind of like, how are you using it and who owns the authentication information? Are you single signing on to some third party, or are you doing it yourself? You can use SAML, I think, just for signing claims, but in my experience, we've used it for third-party identity. Anything else on Discord?
No, other than great talk and every question that came up, you answered it after right away.
So the comment was, every question they had, I answered it in advance. I am psychic. I worked very hard, so I'm glad I nailed it. I cannot see if there's any hands here. So I'm going to step away from the lights. I'll be around if you need me. I'll be on Discord if you want to ask any questions. And again, stock tips to that email address. Desperately need them. Have a great day. Thanks for coming. Let me get back to that.